not saying that. The method tendency. Hello. Yep. Okay, fine. Let us change the topic. What you were studying? You were studying student plasma. Okay. Now let us study Galactic nuclei. What we studied last time? Studied components of it. Before that, we studied the definition of it. What is an alien? Okay. How the story started at all. Fine. So now, since we know what is an alien, so we will go for the next thing. Will be to understand its classification. Once we know human being, then we have to find out how they are classified. Okay. So the old traditional classification is called, these aliens are classified as quasars and cephers. Need you have some urgent business to deal with, please go out and deal with that business. Okay. So this is the old and classic definition that some aliens are classified as quasars and some aliens are classified as cephers. Okay. Quasars, I told you yesterday, they are called quasi-stellar radio sources. Quasi-stellar means why? Because they look like a star, point sources, and they are strong radio sources. So this name quasar appeared. And the Cepher, this name came after the Carl Cepher, the person who first noticed emission line in these galaxies, Cepher galaxies. So the definition, we segregate these aliens on the basis of something called absolute magnitude in B band. Absolute magnitude we have studied. Okay. So if the source is having absolute magnitude greater than -23, so absolute magnitude greater than -23 means the source will be faint or source will be bright. Greater than -20, say -20, -10. It will be brighter or it will be fainter. How many brighter? 1, 2, 3, 4, 5, 6, 7. If a source has a magnitude -10, it will be brighter than a source which has a magnitude, absolute magnitude, say -20 or -25. It will be brighter or it will be fainter? Brighter. It stays stuck into brighter. Okay, fine. We are only 20 minutes late. So, of course, it will be fainter. Magnitude equal to -2.5 log f. There is a minus. Okay, so flux will be larger, magnitude will be lower. Our naked eye limit is 6 magnitude. We cannot see fainter than 6. If a source has a magnitude, say 7, 8, 9, you cannot see. Fine. So cephers usually have absolute B band magnitude greater than -23, and quasars usually have less than -20. But why -23? Why not -24? Why not -22? Okay, we do not know. This is just some arbitrary thing. Fine. But for our class purpose, let us use quasars, aliens synonymously. We will not distinguish them in like cephers or quasars. We simply call them quasars. Okay. This picture you have seen yesterday. What this picture tells us? Manoj. Who is Manoj? There should be a person named Manoj. You are Manoj? What? My father's name is. No, I'm not your father's name. There should be a guy named Manu Patil. What is your name then? Piyush Patil. So there are two Piyush now. No, only one. There are two. There one more Piyush. Piyush Patil, not Manoj Patil. I don't know from where it came to my mind. Whatever. So tell me, anyway, I wanted to ask you only. What is this?
Every energy, whatever the central AGN.
This okay. This is a schematic diagram of an AGN. Okay, you can see a black hole. Everyone can see a black hole. You can see accretion disk. You can see broad line region clouds. You can see narrow line region clouds. You can see molecular torus, and you can see checkers. And you can see moving plasma cloud. They are moving very slowly, so you cannot see them moving. Fine. So let us see what happens. Suppose you are an observer. Okay, you are standing somewhere. I mean, our Earth is somewhere. Fine. So you are located at a place. If I draw tangent from the say black hole center, touching the edge of molecular torus, you understand this molecular torus is like a donut shaped structure. So you have a center. You can draw a tangent. Fine. So you know that if you are standing somewhere, you will see radiation coming from the broad line region clouds, and you will also see radiation coming from the narrow line region clouds. Fine? Clear? So when I say broad line region clouds means what? Broad emission lines. And narrow line region emission primarily it's narrow emission lines. Fine? So the point is that if we take the optical spectrum of such a source, we are expected to see both broad lines as well as narrow lines in the optical spectrum. Isn't it? Fine. You will ask me where is the narrow line? I showed you where it is. The people who don't remember it, let me use the red color. So this line which you are seeing here, this is a combination of a broad component and a narrow component. So you are seeing the sum of everything. Fine. So basically, how do you know whether this is a broad line or narrow line? So I told you that if you measure the width, total width, if it is greater than say 1000 km per second, you know that you will be measuring in angstrom. X-axis unit is angstrom, but you can convert that into kilometer velocity with a very simple formula. Delta V by C, no, delta lambda by lambda equal to V upon C. So delta lambda is the width, lambda is the center wavelength, and V is the velocity, C is the speed of light. Simple formula. Okay. So this kind of sources where we see both broad lines as well as narrow lines, they are called type 1 quasars. No problem. Fine. Okay. Now let us go to a situation where you are standing somewhere else. Like there could be some other AGN whose orientation with respect to our line of sight will be something like this. So you understand in this case what is going to happen? Emission from the narrow line region will reach you, but the emission from the broad line region will be obscured by this torus. Okay? This will be obscured because your torus is like hiding whatever the broad line. So this means torus is much bigger compared to your typical size of the broad line region. It will obscure your vision. So broad emission line, they will not be able to reach you. So if you take the optical spectrum of such sources, you are expected to see only narrow lines. Okay? And such objects are called type 2 quasars. So type 1 are those sources where you see both broad lines as well as narrow lines. And type 2 sources are those where you see only narrow lines. And you will also understand that this will not happen drastically. This change will not happen drastically. Because there is no standard you can say, okay, that see you understand this type 1, type 2 also depends on your this opening angle. How big torus is. Isn't it? In some areas it could be even bigger. This is in a good language it is called covering factor. So if the covering factor is large, suppose it means if this angle is large, so even say at smaller angles, this broad line will be obscured. You will not be able to see. So what people have done, like this type 1, type 2 was a bit old classification. So later on, people started giving the like classifying them as like 1.2, 1.5, 1.9, like that. But the concept is this: depending on the observation or say means presence or absence of broad emission line, we can classify such as type 1 and type 2. Clear? So this is one type of classification. Fine. Now there is another type of AGN classification. So this is something called radio quiet quasars. So as the name suggests, radio quiet means these sources, if you observe them in radio band, they may not be detected. But if you observe them in optical, you will see a prominent emission, broad emission lines, etc. Everything. They will be a normal AGN, but they are just not emitting radio emission. Okay. So that's why we gave the name radio quiet quasars. And we understand that typically this radio emission originates from the jet. Okay, because emission disk is emitting mostly in the optical UV regime because of the black body, which is peaking in the optical UV. So radio band, the flux is very tiny. So you will not detect emission disk radiation in radio band. Radio emission primarily comes from the jet. Fine. So in other words, you can say radio quiet quasars are those AGN that don't have jets. And typically they comprise of about 90% of AGN populations. So 90% of the AGN population is radio quiet. Fine. So now you understand there will be 10% remaining sources which have jets, powerful jets, and they are called radio loud quasars because they are strong radio emitters. When I say radio, I mean typically gigahertz frequency radiation. The radio can have, because radio is not like one wavelength, it's like band, megahertz frequency, gigahertz frequency onwards. So typically we do observations in the gigahertz frequency in the band, gigahertz frequency band.
So why do the jets also radio?
What? Sorry?
Like why do we get only radio waves from the jets?
No, jet emit radiation across the electromagnetic spectrum, not only radio. They emit radiation across the optical UV, X-ray, gamma ray, everything UV. And they emit radio primarily via synchrotron magnetism. I will discuss this thing. Okay, you will understand that why they are strong radio emitters. I will explain that. Fine. So this radio loud, radio quiet classification, everybody understood. So you understand that this is a slightly bit more physically motivated classification compared to your quasar and sequence presence or absence of the jet. Fine. We have absolutely no idea why most of the AGN don't have jets. If you take the optical spectrum of a radio quiet quasar and if you take the optical spectrum of a radio loud quasar, the spectrum may look like a jet. In the strong emission lines, etc., everything. But there was one source is no jet, other source has. It's a very important problem. We do not know. Okay? I will try to address briefly this point later. Now, if you know that in the radio quiet quasars, you can have type 1 radio quiet quasar and type 2 radio. Fine? Isn't it? इसको नहीं समझ में आया. You understood? Last? No? Yes. Similarly, in the radio loud category also you can have two types. Type 1 radio loud quasar and type 2 radio loud quasar. Okay. Let me see who is sleeping. Everybody wake up. Fine. This everybody understood? Awesome. Pucho.
The quasar, radio quiet quasars, we know that. So we are not getting any radio frequency. Why we are like classifying type? Like how we are classifying type 1?
Type 1, type 2 is classification is based on the presence or absence of broad emission lines in the optical spectrum. अभी पढ़ाया है 5 मिनट पहले. समझ में आया? So this classification, type 1 or type 2, it is, you can say it's an optical classification. Optical classification. You take the optical spectrum and then you classify it. So just from the optical spectrum, you cannot say whether this is a radio or radio point. Yeah, you cannot say that because you don't. For that, you need radio observation. Because radio observation will tell you whether the source is detected in the radio band or not. Okay. Now see, I am telling you a very simple picture. Real picture could be more complex in the sense. Suppose if the source is nearby. Nearby means it's below let's say 0.5, 0.4. And if there is lots of star forming activities is happening in that particular, because you see the whole galaxy is there. This what is photo you are seeing, this is the central part, but the whole galaxy is there. Suppose if there are lots of star forming activities are happening there, then star forming activities also emit some radio inside. So how will you know? So then people came up with some correlation, radio IR correlation. Correct? When you try to calculate the luminosity of the radio flux and the luminosity of the source in infrared, and then you see where your source lies. If the radio luminosity lies well above than this correlation, then the radio emission is primarily because of the jet. So see, this means this is more complexity is there, but here we are limited up, keeping outside limited to simple picture. Okay. Now let us talk about something called AGN unification. No, but emission line, I told you that, man. Usually galaxy have stars and stars primarily emit absorption. They have absorptions. So emission lines will be mainly emitted only by broad line and narrow. There is nothing else which can emit strong emission lines. Okay, you understood now? Because the rest of the galaxy is like a normal galaxy. So the rest of the spectra, whatever you DC, will be like absorption spectrum. Fine. So you see that spectrum I showed you, this is dominated by emission lines. In principle, if you ask me, like really, there will be absorption features also because the galaxy has lots of stars. But those absorption features will be like a swamped by the strong emission lines. You are not seeing those absorption features. In some galaxies, we do see absorption features as well as emission line features. Sometimes we see. Specifically if the galaxy is nearby. Because nearby means what? Like the source will be brighter. You can detect the host galaxy. Host galaxy means the galaxy in which this region is there. Fine. Okay, let's go. Okay, so there's something called AGN unification. So we are unifying AGN. So what is the meaning of that? You know that we have classified AGN with different types, different names. How will we classify AGN with different names? Name? Yes. So that I am writing in a different type. I am asking about names. Shivansh. Who is that Seaford? Made by name? Seaford is the name of some guy on whose name this name Seaford Galaxy is. Okay. So, but we have to understand that these AGNs, they are really one type of sources. They are, so when I am telling you that radio quiet quasar or radio loud or say type 1 and type 2 quasar. So you understand that AGN is not different. AGN is like one only. But what is happening? Their appearance changes because of their orientation with respect to our line of sight. So in some AGN, we will be looking directly through that torus. They will look like type 2. And in some other case, some other AGN, because in the universe, galaxies are oriented, they are oriented random direction. There is no preferential direction, no, all galaxies will have only this particular jet in our sight. It can be any direction. So some galaxies may have, we are looking close to edge on view. Understood? You consider the whole galaxy like a plate, that torus. So some galaxy you are observing like an edge on view. Some galaxy you may be looking at a pole on view. Pole on view means you are going toward the type 1 source. Fine? I will repeat this again. This is called AGN unification. So you understand the meaning that AGN are one type of sources. They look different because of their different orientation. This is called AGN unification. I will give you one simple example of this first. Let us consider an elephant. And there are some blind men. So someone is touching the ear of an elephant, and the fellow will think, if someone asks what is an elephant, so it will say it's a fan. Someone is touching the leg, so the fellow will say, if I ask what is an elephant, the fellow will say it's a tree. So this means while from the different directions, the same object look different, but it is the same object. In the same fashion, AGN, they are same type of sources, but they look different. So say for example, I'm going to explain some of these terms, but if you are close to this pole on, you can say this axis, perpendicular axis, you are observing a type 1 quasar. But if you go close to the edge on view, you are observing a type 2 quasar. Some sources have jets, most of the sources don't have jets. But type 1, type 2 classification can work in that. Fine. I will be focusing mostly on the sources that have jets because they are rare. Okay. So
that is pointed towards us, that we see absorption and
coming to that. I'm coming to that. Okay? Because anyway, rest of the presentation I will be talking about jet axis. Okay. So when we are looking close to the jet axis and the source had jet, powerful radiostic jet, we call the source blazar. So blazars are type 1 radio loud blazars with jets pointing directly toward the observer. Shall I repeat? But anyway, they are recording. So all this, whatever I'm speaking, you can find on YouTube. So see, first we are close to jet axis. This means the source is type 1 source. And if there is a jet present, those source will be radio loud source. So type 1 radio loud quasars whose jet axis aligns with our line of sight are called blazars. All these terminologies came in late 1960s, 1970s. Fine. And suppose the same radio loud quasar you are observing from a very far off, then we call the same source as radio galaxy. Just a name, radio galaxy. Radio means they are strong radio waves. So blazar means our line of sight aligns with the jet axis. In radio galaxy, jet is pointed some random other direction. So if you can somehow travel towards the jet axis, the same radio galaxy will become a blazar. Isn't it? Understood? Fine. So let us, in the rest of the talk, I will be discussing only these two, blazars and radio galaxies. Basically, I work on blazars mostly. Fine. So first, let us talk about radio galaxies. So you understood type 2 radio loud quasars that have relativistic jets pointed away from the observer. Observer means Earth, but observer can be anything. Some alien can also be observer. They are called radio galaxies. This is a real picture of a radio galaxy, and I am going to explain this later. But for the timing, I will tell you. You see this fountain-shaped thumb structure. This is the jet. So basically, this picture is a combination of radio image plus optical image plus X-ray image. You are seeing bluish color like this, some foggy structure, that is X-ray observations. You are seeing this dust lanes, this is optical observation from Hubble Space Telescope. And the jets you are seeing, this is radio observations. Okay, I will discuss this specifically this picture later. And these stars you are seeing, most of these stars are the stars in our Milky Way. Foreground stars. They are not in that galaxy. Okay. So the typical viewing angle with respect to jet axis is usually greater than 30 degrees. But it's like understand, it's no written rule. No, if it is 29 degrees, then it's not a radio galaxy. I recently published a paper claiming that the viewing angle is 15 degrees, and I still said it's a new galaxy. It got accepted. So it's like it depends how you are explaining, how the observations are like helping you in classifying the source. But you can say for the certain, if the viewing angle is greater than 30 degrees, definitely it's a new galaxy. There's absolutely no doubt. Okay. The typical radio luminosity of these sources are 10 to the power 42 to 10 to the power 46 arcs per second. And radio emission is due to synchrotron process. And I will briefly discuss this later in this class. But I am sure in the radiative process course you would have studied this. Synchrotron, Compton scattering, and everything. Fine. Okay. Their host galaxies are almost exclusively elliptical galaxies. So radio galaxy is nothing, it's not a full galaxy I'm talking. It's a central region where you have AGN. So when people try to observe that what is the morphology of the rest of the galaxy that have such sources. So they found that typically these radio galaxies, they are residing within giant elliptical galaxies. So you understand, it's like yesterday I showed you a video when we were traveling towards a galaxy, one AGN. So you saw first it looks like a normal spiral galaxy. So it's like that. Suppose if you travel towards a radio galaxy, first you will see a big elliptical galaxy. But if you keep traveling towards the center, then at the central region you will start seeing the jet, accretion disk, broadband region and all. Got it? So why I'm emphasizing on this point, because in the galaxy course, you were taught that how elliptical galaxies are formed. Somebody told you about galaxy mergers. Okay, so elliptical galaxies are usually formed via mergers. So that will, I'm trying to connect the dots in the fashion that we are proposing. Like I wrote one paper on that. That probably to understand you need high resolution imaging. If you want to do imaging, you will use optical observation or infrared observation. Because we will see traces of mergers. It will not happen that merger happened and everything was lost. You will see only because this activity will keep happening for millions of years. So the fifth type which I shared with you, where you saw this spiral kind of structure, that was not a spiral arm, that was a tangled trail. It's like two objects merging each other. Okay, so they will start like it's like something is, you might have seen some video where some star is being pulled up close to by say black hole, then start debris with a debris. It follows the trail. That is called tangled trail. So in the galaxy also we see that some signature events. And since we have seen in so many cases, so we believe probably that all elliptic galaxies are formed via mergers. Okay, fine. Now radio galaxies have its own structures. Let us see one by one. First, there is a core. So see, I am talking in the radio band. Here, whatever I am talking about the radio observations. I am not talking about the optical broad line region, narrow line. Everything is there, but I am talking only about the radio observations. In the radio observations, in a radio galaxy, typically we see a core is means like a central within kiloparsec region, which will look like a bright point source. Okay, the whole galaxy might be within this point. Then we have something called jet and counter jet. So you see this linear structure. This is the jet. You can understand. I told you it's a collimated relativistic flow of plasma. And when I'm telling it is a jet, and when I'm telling it is a counter jet. So you have studied relativistic beaming. Beaming was taught in radiative process course. Beaming. No, I will teach. Don't worry. So the point is that, I'll briefly tell you. See, whenever a train is traveling towards you, if it sounds, so the sound will appear of a higher frequency. Doppler effect. So try to for the moment try to understand in a fashion that suppose the jet is slightly misaligned, but it is suppose it is moving towards you. It is not exactly towards you, some 20-30 degree, but still moving. So the jet will appear brighter compared to the other side, the jet which is going away. So the jet which is moving towards us is called the jet, and the jet which is moving away from us is called counter jet. So in this figure, you can understand this is the jet and this is the counter jet, because counter jet is much fainter compared to this side of the jet. Okay, and exactly this happened because of something called rate cleaning or Doppler boosting. I will teach briefly. I will teach. Then they called lobes. What is this lobe? You see this diffuse blobs. This is a radio image. So this entire is radio emission. Okay, this entire structure is called lobe. So you can understand what happens as the jet travels. So as you are going away and away from the center, slowly magnetic field strength will decrease, because magnetic field is produced by that accretion disk and black hole interaction. I didn't show you a video yesterday. Okay, I have it. If you like, I can show you. It's like people did numerical simulations. Suppose you have an accretion disk, which is black hole. Now, in the t equal to 0, you thread this accretion disk with vertical magnetic field lines, like a straight lines. Okay? Say, for example, this is a black hole, this is accretion disk. You thread magnetic field lines at t equal to 0 like this. Say, for example, ideally it doesn't happen, but for example. And then you allow the system to evolve. This means now you allow this accretion disk to rotate. So you understand your magnetic field lines will start twisting. Okay? The picture will not be that easy to understand, but you are getting the point. This simulation, what I am talking about, that's how people have proposed that this magnetic field plays an important role in launching the jet. That's how magnetic field becomes spherical. If you recall one cartoon I showed you, magnetic field in the jet was having this kind of structure. So this magnetic field has some pressure, magnetic pressure. It tries to compress the jet, and the particles, plasma change, they try to go up. So as long as this is in balance, the jet will remain collimated. But you understand, as you go away and away from the black hole, your magnetic field strength will decrease. Fine. So ultimately, who will win? Particles will win. So ultimately, you understand, at the end of the day, the jet will slowly will diffuse. Now you understand the origin of lobes. And by the time the jet, like this matter, reaches to the lobes, its velocity becomes almost, like you can say, very negligible. It's almost static. So since the particles in this lobe, they are not moving, more or less they are stopped. So no Doppler effect, they are not moving. So no beaming, nothing. So that's why you see the lobes they look equally bright both sides. They are not, that's like isotropic radiation in all the directions. Even the lobe which is on the other side, that also looks equally bright because it is not moving. If it would be moving with some velocity, it would appear fainter. Understood? Concept, you understood? Concept. Now there is something called hotspots. So hotspots are those regions where this jet hit the intergalactic medium. Intergalactic medium is not empty. It's not completely fully empty. There are low density plasma, gas, dust, everything is there. So you understand wherever this jet will hit the intergalactic medium, that's where the radiation will be bright. So we are calling them as hotspots. Shall I repeat it? So suppose it's like you throw some water, you have water pipe, you throw water. Okay, your water is flowing, but suppose you hit against this wall, or you have some dense medium. So wherever this water will hit the dense medium, it will spread. And that spot where it is hitting it will appear much brighter. That spot is called hotspot. It's just a terminology. People give them name. It does not mean that spot is very hot. Just name is hotspot. Okay? Got it? Fine. So there are two scientists named Fenroff and Riley. They proposed radio galaxy classification scheme based on the radio power. And so on their name, this scheme is called like the radio galaxies are classified as FR1 and FR2. FR corresponds to Candroff and Vaidehi on their names. Okay, I think they gave in 1970, 75 something. So FR1s are those sources whose radio power at 178 megahertz is less than some number. Okay, fine. So you can, if you try to understand, this is not a, it's not truly, it's not a power, it's a power density. You have per hertz. Like flux is say ergs per centimeter per second, but if you have per hertz, it becomes flux density. And FR2s are those sources which are more powerful. Okay, and later when the resolving capability of instrument improved, then we started seeing that morphologically also these two sources, these two types are distinct. Let us see how. Okay, this picture I was showing you so far, this is a FR2 radio galaxy. Okay, so you can see jet, counterjet, lobes, and first pass. If you see these features, the source is a type 2 source. Sorry, FR2 source. Okay. Now FR1 radio galaxies, they show this kind of structure. First of all, they do not show hotspots. You can see that this look here, it looks like the jet maintains its energy and ultimately jet is depositing its energy into the intergalactic medium. Here it looks like the jet is losing its energy while reaching large distances. It loses most of energy while going itself. So rather than seeing bright lobes and hotspots, you will see plume of radio emission. They are called FR1 radio galaxies. Now don't ask me why. You will have no idea why it happened. Isn't it? You can, yeah.
What is so special about the 178?
No, so because at 178 megahertz, those people observed. You observe at gigahertz and you give your own classification. But they were the first, everybody follows. Just like that. Like Sifat and Kueja, minus 23. Somebody here, so we are just following. Fine? Now I'll show you two more pictures. You understand? This is a part of variables. Now you can, so if I give you some problem, or if I give you a set of images, just by looking at the radio morphology, you can determine whether it's a FR or FR2 source. Isn't it? You can do it. Okay? You will do it. I will give you for that. Not to do this classification, but you will find means I will give you radio images where you will see these structures. Okay? You understand? This is a FR1 galaxy. But other than FR1 and FR2, one more thing you have to see is that you see that jet does not look like a straight line all the time. You see it looks. And in some radio galaxies, we have also seen like this is the central core, and the jet is like this. It looks like the galaxy is moving in this direction. Suppose you are running and you have something in your bag, what it is called? What is something I forgot its name. It will be flowing in the bag. You got that? So you are running something and then your hairs will start flowing back. So like so the jet goes back. The galaxy itself is moving somewhere. It happens, we have seen all these things. Simply search in Google about this head-tail galaxies. Head-tail galaxy, wide-angle-tailed galaxy. These are the different types of radio galaxies. Alright, let's come to breakouts. Finally, we have only 20 minutes.
What happens in F1 because of which we get flumes and not lobes?
Yeah, so that is we don't have a clear answer. In some of the radio galaxies, we see one side they show FR2 structure, means hotspots and lobes, and the other side we just see plumes. They are called hybrid morphology radio galaxies, or called HYMOS. HYMORS. HYMOS. So you understand, like I am telling you a very simple picture, but the reality when you start working on, when you do PhD or research on these topics, the story becomes much more complex. We have absolutely, I will tell you that some people have given the idea. It's not like that we do not know anything. But then what people did, they try to understand the surrounding medium of such galaxies. So they found that usually the FR2 radio galaxies, they reside in denser environment. So when you have a denser environment, it is highly likely your jet will interact with the medium, and that's where you will see lobes and hotspots and all. FR1 usually they are mostly like they are lowly. The jet only has to do this. I think there is nothing else to do. But this is not true for all sources. Okay, so there is no universal answer for this. That's what I want to do. Okay, let's come to quasars. Okay, from the radio galaxy, let us move towards the jet axis. Fine. So as I told you, type 1 radio loud quasars that have jets pointed towards the observer are called quasars. So you imagine you have a galaxy. If you take a look at the central region of the galaxy, you will have a black hole, accretion disk, clouds, torus, and jets, and you are standing and observing instead. Like this. This is the configuration I have got. Fine. These sources are called quasars. We are looking directly into the jet axis. What exactly means that this viewing angle with respect to jet axis, save mind. The point is that suppose if the jet axis is something like this, and suppose you are observing from here, means your angle is something like this. So this angle, you understood? Jet axis, and from where you are observing it, this angle is called viewing angle. Typically in blazars, this is between 0 to 10 degrees. Okay. Now, I told you that about 90% of the AGN don't have jets. So this means only 1 in 10 galaxy AGN have jets. So even and among the sources that have jets, this is not guaranteed that all of them will have jets pointed toward. Jets can have in any direction. So about less than 1% of those sources that have jets will have that jet pointed towards the observer. So this you can do simple calculation also. You assume a situation. Suppose you assume this is a sphere in the universe, and this is a galaxy which having jet. Okay, so jet, I am telling something like this. So you can determine this cross-sectional circle area. How you determine? Suppose if you know this viewing angle. Okay, I will tell you it is easy. You can do it. So the point is that you want to determine that what is the typical number of sources that have jets pointed towards us. What you have to do, you will have to divide the whole sphere area by the area of this. That's it. Suppose suppose you are standing here. So whenever your line of sight is passing within this circle, the source is a blazer. Rest everything will have this area, whatever the jet cross-sectional area, some other direction. So you divide the overall area by your area. So you determine how many sources will have jet in my direction. So it turns out that typically less than 1% of known radio loud AGN have jets pointed towards us. So you understand blazars are so rare sources. Idea like, yeah, chalo. But the question is how do we know that we are looking into it? The first question comes to our mind. How do we know it? Because we do not see jet like, oh, it is coming towards us. They are not so nearby. They are so distant. Like you see this photo I showed you, this galaxy. Can you tell me that what is the viewing angle? You cannot say anything. Just by looking into this picture, you cannot say anything. Isn't it? So this means we have to determine how we know that we are looking into the jet. Then there is something called superluminal motion. Okay. So this will be covered in detail in the relativistic jet class, which Professor Satya will take. Okay, so I will just touch. So you consider the situation here. Suppose this is a distant quasar. Okay, look at the photo. Carefully look into it. And suppose this is the jet in the 3D sky. Fine. Suppose if jet is moving in this direction, but if the universe is so big, for our imaging, the sky always looks like a flat plane, which you see here. Okay. So suppose if I am an agent, you are observers, whatever suppose C is the, or suppose this camera is the observer, and suppose if the jet is going in this direction. So you are as an observer, you will see this plane. Understood? This plane, whatever you will see, or everything. You will not see what is you will not be able to recognize that something is coming from behind to front. You will see something in moving. Now suppose if this that plasma blob or jet is moving in this direction, it will have two velocity components. One is along the line of sight, exactly along the line, and one is perpendicular to the line of sight. So the motion due to the motion along the line of sight will not lead to any change in the image. Because you understand, I suppose I show you this time. It looks like a point. If it is exactly moving towards you, it will always remain a point in the sky because the distance is so large. Fine. So the only motion that you will recognize in your image is the motion due to this perpendicular component. So that point I want to tell you that if suppose reality is the jet is moving in this direction, it will have two components. So the motion due to v cos theta will not lead to any change in your image. But motion due to v sin theta, you will see jet is moving in this direction. अब समझ आ रहा है? Jet is really moving in some other direction, but you will see it is moving this way. Because the motion due to this way, you are not able to see any change. Fine? Put in understand, no problem. We can talk it out. Alright? So if this is the case, actually this I will show you a real photo. So this is I will show you the photo of this. See, this is the jet of famous AGM M87. Okay, it is a radio galaxy. M87. This is the M87 jet. So since it's a very nearby source, so we were able to resolve the features in the jet, and then over the period of time, we have seen that these features move. So this is my 2D image. So I am seeing that plasma knots, they are moving. Fine. So now what people have found, when they did the calculation, that in 6 years, the plasma knot, they picked one knot, which was very bright, it traveled 24 light year distance. What will be the speed? In 4 years, if the plasma traveled 24 light year distance, what will be the velocity? 6 times speed of light.
So isn't plasma ionized gas, then it has mass?
So
How can a particle having mass accelerate and like have a speed greater than?
so this is the question. This is the question that is coming to your mind. It came to mind and this answer. How velocity can exceed the speed of light? So this means something is wrong. But your observations are correct, your measurement is correct, everything is correct. So why it looks like it is moving, it is velocity 6 times the speed of light. So this is like, I will give you a kind of homework for you, but this is a simple geometric effect. If you do a calculation that in 1994, the radiation emitted, and in 2000, by suppose it is coming, suppose for example, you are located 6 light years away from that source, say for example. So in 1994, the radiation emitted when the quasar was here. Okay. So in 2000, when the radiation reaches you, but the quasar itself is moving, the jet is moving. So in 2000, the jet will be somewhere here. So now the radiation which it needs to emit, it has to travel 4 light year distance less. ज़्यादा हो रहा है. We look at difference. That's too much. That is too much. Let me come. Okay. I just have 10 minutes, so that's why you try to read about. Just search in Google superluminal motion. And okay, so let me try to very quickly summarize it. In 1994, the jet plasma emitted some radiation. The radiation is traveling with the speed of light. Okay. So this pulse of light reaches Earth in 2000 in 6 years. Okay. Now 6 years later, I am telling, suppose my that jet plasma drop, it is somewhere here. Fine. So second pulse of light emitted 6 years later, but has 4 fewer light years to travel. Reaches Earth 2 years after the first pulse in 2002. So this means when the first pulse was emitted, it reached 2000, and when the second pulse reached Earth, it reached in 2002. So for in your reference frame, the time spent is 2 years. This you understood? So if I tell you total distance was 6 light years, this is 4 light years. Okay, and you will see that in your plane that it has traveled 3 light years. Okay, so what you will see, as an observer, you will see this distance traveled, and what is the time span? 2 years. So what velocity you will think? This distance divided by time. So you will see that apparent velocity of that plasma is moving is 3 by 2c. So you will see that plasma is moving with speed greater than speed. But actually what is happening? Plasma has traveled 5 light years in 6 years. So the real velocity is 5 by 6c. So you understand this, whatever this phenomena we are seeing, this is happening only because this plasma is moving towards you. So you understand that the smaller this angle, the more apparent velocity, faster the apparent velocity you will see. Why? Because the denominator time will be smaller. Got it? This effect is called superluminal motion. So reality, it is not moving with speed more than speed of light, but it appears. And this appearance is a conclusive evidence that the plasma which is moving very close to your line of sight. Got it? So suppose if you do the superluminal motion measurement, and if you can measure the velocity, and if it is a super luminal, means more than the speed of light, then you can say this source is probably blazar. So in fact, people have carried out this study for so many blazars, and they found yes, blazars do show superluminal motion. So who will tell me whether radio galaxy will show superluminal motion? Yes or no? How many yes? How many no? What about rest? In radio galaxy, we may not see. Because why? Because in radio galaxy, we are observing very off axis. Jet is in this direction. Plasma moving in this direction, not towards. So this angle is very large. So whatever you will see a small movement, you may not see any recognizable. Clear है? चलो आगे बढ़ो जल्दी से.
Sir, actual velocity calculate कर सकते हैं.
क्या? देखो, भाई बस इसी. Yeah. So you see, you can measure the viewing angle and then you correct. You apply your corrections and you can calculate. You can do it very simple. But when a charged particle is moving with relativistic speed, so what happens? Most of the radiation, which was earlier, suppose this is a charged particle, it will emit radiation in all the directions. More radiation. And when it is moving, so what will happen? Most of the radiation is confined to a cone. This is a very simple derivation. I don't have time for that, but it's a very simple derivation you can do. So what happens if a charged particle is moving with relativistic speed? So most of the radiation it will be confined to a cone, and the higher the velocity, smaller the cone angle. Means like it will become more and more like a pencil beam. So you understand? For earlier, you suppose if the charged particle at rest, you were receiving 1 unit of flux. Now charged particle is moving towards you and you are receiving 49 units of flux. So the source will appear brighter. This effect is called relativistic beaming. The radiation is beamed towards the observer. Okay? This is called relativistic beaming or Doppler boosting. So it's a kind of like a Doppler effect you can think about. It's not exactly a Doppler effect, but for your understanding. Okay? So you understand it enhances the radiation by factor of 10 to the power 4 to 10 to the power 5. In other words, an optical photon may become a gamma photon. So when it was originated from that charged particle, it might be an optical photon, but because of this motion, the frequency of the emitted radiation increased. So you see it gamma. Okay, but this is important only when the charged particle is moving with very high velocity towards the observer. Suppose you are the observer and the charged particle moving in this direction, you will not see any enhancement. Only the observer will sitting there will see the enhancement. Fine? You see, everything is viewing angle. So now you understand this means, and you see in the AGN they have jets, jets have plasma have lots of charged particles, electron, protons, etc. They are moving with relativistic speed. So you understand in blazars, since you are looking directly in the jet axis, this effect will take place. Question? Just 5 minutes. Let me try to finish. Okay? समझ में आया? So this means an intrinsically faint quasar may appear extremely bright if it has a jet pointed towards you. Because jet means what? You can understand like this radiation. So it is moving towards you. So most of the radiation will be confined. And if you fall in that cone, you will see enhanced radiation. Fine? Now just keep in mind, this effect is happening only because of the motion of the plasma. Okay? So suppose in the AGN there is accretion disk, broad line region, torus, etc. But those entities, they are not moving towards us, isn't it? Means they are not moving with relativistic speed. So this means the accretion disk radiation or broad line region radiation or torus radiation will not be boosted. Okay? Only the jet emission will be boosted. Why? Because the jet is moving. Jet means plasma. That plasma is moving towards you. Clear? Okay? Don't worry too much. If you want, I will share the slide. Even don't worry. Just it's really interesting results. Okay, so this I have already told you. So the point is that even among the AGNs, okay, the sources that have jets pointed towards you, the jet radiation coming from the jet will overshine the radiation coming from the rest of the accretion disk, BLR, etc. etc. Jet emission will be so dominant. Okay? Jets are the most powerful persistent source of radiation in this universe because of this relativistic motion. Okay? Got it? See, jet emission is so dominant. You will see some disk emission sometime. Sometime you will see, sometime you may not see. Forget about the host galaxy. Forget that. It will be neglected. Okay? Alright. So let us quickly go through some radiative mechanisms that power jets. The radiation which is coming from the jet. So everybody knows synchrotron. So you know that in the jet there is a strong magnetic field present. And these is very relativistic charged particles moving. So in the presence of magnetic field, these charged particles will radiate via synchrotron. When we call synchrotron and when we will not call it synchrotron? When the velocity of the charged particle is relativistic, then the emitted radiation is called synchrotron. And if it is non-relativistic, then what we call it? Cyclotron. Fine? Okay. Accelerated electrons will emit radiation. In the presence of magnetic field, charged particle will be accelerated because of their motion. And an accelerated charged particle emit radiation. This we have studied in radiative process course. Okay? Now let me show you some mathematical formula. Like it's like Planck's law, black body spectrum. So similarly, you can also calculate the synchrotron spectrum. it doesn't look like very simple thing. It's like you have an integration, there are so many terms, you have magnetic field. And what is Rx? I will not go in detail. Rx corresponds to the distribution of charge particle in that region where which you are considering. See, all charge particle may not have same energy. Na? Some will have less energy, some will have more energy. In a good language, we can say the particle population energy distribution of the particles are following a power law. That's it. Okay, so you usually in the jet, these electrons radiate synchrotron emission from radio to optical UV band. Okay, so if you are detecting a radio emission, optical UV radiation from a laser, most likely it is coming from the synchrotron process. So another defining property of synchrotron emission is the polarization. If you put up a polarimeter and you observe the source, and if you detect a significant polarization, say in optical, most likely it is synchrotron. Because thermal radiation is not polarized. Okay? Inverse Compton, everybody knows. So in the Compton scattering, what happens? Low energy electrons and high energy photons. Usual Compton scattering, photons lose energy there. Photons, okay? And the inverse Compton, the reverse will happen. Photons will gain energy. Okay? Now the question comes, for all the, that highly energetic electrons are present in the jet. So for the inverse Compton scattering to take place, you need low energy photons. Isn't it? Electrons are energetic, they are there. You need photons, which can be upscattered to high energy. So question comes, from where the low energy photons we can get. So first of all, I will show you a zoom up version of that blob. See, I am showing you a plasma blob, BFP. Okay, and in that it is filled with electrons. These electrons are emitting synchrotron radiation. So you understand, this synchrotron photon, it may be traveling here and it may hit some other electron and can get scattered. Isn't it? See, the medium is same, na? Suppose in this one some fight is happening. So you hit somebody and over there, someone else will hit that way also, na? Okay? So you have emitted synchrotron radiation, but that synchrotron photon, while traveling, maybe it may interact with some other electron and can get upscattered. Inverse Compton. Okay? Since in this case, everything is happening within the blob. You are not talking anything from outside. Okay? This process, okay, this I told you, this process is called synchrotron self-competence. Because the same population which is emitting synchrotron radiation, the same population is also upscattering. इसको बिल्कुल समझ नहीं आया. Everybody understood? Right? So you see, I told you that suppose I'm an electron and I have just emitted a synchrotron photon, and this plasma blob is like this room. Okay, I have emitted a synchrotron photon. The synchrotron photon is going in this direction. Okay, but before it could go out, okay, it was hit by someone else. So suppose originally its energy was say optical energy. I emitted an optical energy photon, but it interacted with Shivansh and it became a gamma ray photon. Okay, so why synchrotron self-compton? You see, everything has a meaning. Synchrotron, because you are upscattering synchrotron photons. Self means the population, this room, which are emitting synchrotron radiation, the same population is also upscattering. And since the Compton scattering is taking place, so we call synchrotron self-competence, SSC. Okay, let me very quickly show you. Okay, so this SSC radiation can explain X-ray to gamma ray radiation. You know that we have a broad line region, torus, accretion disk, etc. Everything here. I didn't talk about that. Okay, so they are also emitting radiation. Accretion disk emits mostly optical UV radiation. Torus emits infrared photons. These photons can also come into the jet. It's like you are moving with very high speed, and just you came out of that and you found some low energy guy there, and you just pick that up. Fine. So this means I'm in the jet. I'm moving with high speed. I'm kicking whatever I'm finding. So someone comes from outside and kick that out there. So the BLR photon, accretion disk photon, or the torus photon, everything can get upscattered. So now you see in this case what is happening. My source of photons are outside the jet. So this process is called external computer. Okay, and this also explains the X-ray to gamma ray radiation. I will show you quickly some mathematical details. I will not go into detail here. You can calculate the synchrotron self spectrum flux as a function of frequency. And you see, this is a double integration. And you understand for every synchrotron photon, you have to calculate synchrotron self count. And synchrotron itself, you are calculating separately. So basically, this is a triple integration. Though it looks very complex, but you can one. I have done it. If you one can do it. Okay, so that's how we calculate the spectrum. That's how we do modeling. Photon will not tell you that I am coming from synchrotron self count. Photon is a photon. A gamma ray photon is a gamma ray photon. It will not tell you I am coming from synchrotron self compton or I am coming from external compton. That you have to understand. Fine. External compton picture is given. Fine. Okay. So I will tell you very quickly. This is the broadband spectral energy distribution of a blazar. In this diagram, on x-axis we have frequency, on y-axis we have flux, on the other y-axis we have luminosity, which you can multiply 4 by d square, you can get the luminosity. Data points corresponds to observations. You observe the same source at different instruments, and you measure the flux, and you plot the flux as a function of frequency. This is called spectral energy distribution, or SED. Okay. Now lines are model: synchrotron, inverse compton, multicolor black body. For equation this, you remember I told you yesterday, multi-temperature. Okay, equations I showed you last slide and the previous lecture also. And in my PhD, I have developed the model, solved all those equations. So line machine is, this line is my model. So you got some observations and you got some model. Fine. So first of all, before we do that, first one thing you should appreciate that these blazars emit radiation right from low frequency radio waves up to very high energy gamma rays. You see how many orders of magnitude covers. Okay. These blazars are one of the rarest astrophysical objects that emit radiation across the whole electromagnetic spectrum. You talk about the sun, mostly optical UV. Sometimes some flare happen in the same part of the sky you observe in optical, it will be filled with stars. The same part of the sky you observe in X-ray, you find one or two sources. And most likely they will be blazar. Okay. Yesterday I was talking about some agents that emit more energy per second than that emitted by sun in entire lifetime. Blazars. Every moment they emit more energy. If you compare the size of size of the sun compared to the cross section of the jet, okay, it's like 1 pixel. Just like that. Okay. And you see, the important thing is that, and you see, then what I did, I changed my model parameters, etc., in such a fashion so that my modeling is reproducing the observations. You can see, I write it here in this picture that my somehow, see, the blue is the sum of all radiation. Synchrotron, self, because you are receiving some of everything. You cannot say that today at 8 p.m. I will receive only synchrotron and tomorrow morning 9 o'clock I will receive only gamma. You are receiving some of everything. Okay, so you do modeling. You see, my synchrotron self compton is not even reaching to the data points, but with the combination of corona, synchrotron self compton, and external compton, the some blue is passing through X-ray. This is the X-ray band. This is the gamma ray band. This is the optical UV, infrared. Fine. So this brings me to the question of multi-wavelength observations. This is what that's what is happening now. You cannot, if you are studying a source in a certain particular band, which is okay, but it will not provide you the whole picture. If you want to study a source, like you completely want to understand the science physics of a source, you have to go for multi-wavelength observation. I will show you very quickly one very simple example of this. You have seen this photo earlier. This is a radio galaxy. Its name is Centaurus A or CEN A. CEN space A. You can search in Google about it. Centaurus A. There is Centaurus B also, but let us not talk about that. Fine. So see, if you observe the source in visible light, it will look like this. You can see dust layer, etc. You can see some bright bubble kind of stuff. This is an elliptical galaxy. Okay. Now the same source I am observing infrared. It looks like this. Okay, one thing you see, there are so many stars. Where do stars went? The stars are there, but stars black body radiation is peaking in optical UV. So in infrared, they are bound to be very few. So stars are there, but they are just not emitting that much radiation, or their radiation will be below the sensitivity of our instrument. But you see the same galaxy, how it looks in infrared. Whereas though dust layer is gone, because in infrared photons can penetrate through that dust. They are less scattered. Okay. Now the same source, if we observe in X-ray, see how it looks. You have started seeing some feature, some special feature. Okay? And the same galaxy, if we observe in video, what happened to the rest of the galaxy? So you understood the same source, it looks different in different energy bands. Isn't it? Like I am teaching you, everybody happy? You work with me. Different picture. Simple thing. Got it? Multi-level observation. Now, so important thing here is that you have to combine everything to get the overall picture of science, overall picture of EGS. This is the importance of multi-level. Okay, got it? Now, last. So you see, we have a plethora of satellites just to do this. So this means to observe the same source, I write 5 proposals for 5 different observatories, and sometimes I put a constraint. The source should be observed simultaneously. Why? Because the source might be variable. Today evening its flux is something. Tomorrow morning its flux may be something different. Okay. For example, what I mean is that in this figure, suppose today you observe the soft X-ray part, you got this flux. But if you are not observing the hard X-ray simultaneously, tomorrow morning this hard X-ray flux may be somewhere here. But you will not be knowing. You will model, etc. You will make some science out of it without knowing what mistakes you have done. That's why, because blazars are highly variable sources. Okay, so it is very important to go for simultaneous observation. But you know, coordinating so many observatories is always a challenge, and that needs to be strongly justified. But that's what we do. Okay, fine. Last part, summarizing everything. We talked about components, etc. Let's talk about overall life. So see, you might be wondering why not all galaxies, including our Milky Way, are engine? Why we see only small, tiny fraction of overall all galaxies are engine? Why not all of them? Are alien intrinsically different galaxies? These are the questions. Okay? So the question is, are they intrinsically different? Possibly. So what people have gave the idea is that astronomers that who are studying galaxy evolution. See, like our life evolves in the same fashion. Star life is also evolves. That I taught you. Similarly, galaxy also evolves. Anyway, so people have proposed that this AGN phenomenon or AGN activity, when the accretion is happening, jet is launched, etc. This is a certain phase in the life of the whole galaxy. So then, in other words, our Milky Way might be an AGN sometime in the past. Because today it's a normal passive galaxy, not an AGN. Means something might have triggered some AGN, we do not know. Okay? So the question is that, do we know whether our Milky Way ever had an active nucleus in the past? See, in astronomy, we can never give a definite answer. Because we do not know. But possibly. Let us see how. So I will show you only a couple of pictures and we get it. This is the gamma ray image of our night sky. But it is, I am plotting in the galactic coordinates, so you are seeing slightly this kind of structure. It depends on what coordinate system you are plotting. Fine? So are you seeing something coming out from the center? Some two structures? Something? Okay? They are called Fermi gamma ray bubbles. They were discovered in 2008 or 2009 when Fermi gamma ray space telescope was launched. Okay, when our sensitivity of our instrument was that good, we could detect these things. We started seeing the features. You are seeing something here? Fine. Now, just a few years ago, another mission was launched called IUCAA. It was launched by, it was a combined German-Russian mission, and they ordered the same part of our Milky Way. Our Milky Way center is here. You see this dust lanes, etc. See the dust lane along the lines. Are you seeing some features here? When we try to combine everything, we see things. So people have proposed just like a model. People have given a model that these excellent gamma ray bubbles might be remnants of the AGN activity happened in the past. See, I told you yesterday that suppose you are standing in a football field and you kick a football will go, and you just hold for some time. Does it mean football will start immediately? Repeatedly. The same thing here, this energetic particles were kicked out by that active black hole. Now slowly that black hole became dormant, but those charged particles are still going. They are emitting X-ray and gamma ray radiation. That's why you see this X-ray bubble is larger than gamma rays. And gamma rays are more energetic. So the higher energetic photons will lose energy faster. If you turtle and rabbit days. Understood? Turtle will go further. Okay? So let us summarize what we have done in the last two classes. We have learned about bit about what are regions, bit about the history, bit about alien components, bit about sources that had checks, and we have learned a bit about the life of an agent. Okay? Now I will finish by showing this photo. Now tell me who does not understand this. You don't understand? You understand? Shivan does not. You understand? You will explain to it. Not right now. Everybody understands this now. These are BLR clouds. It's a cartoon anime. It's not a real photo, man. Okay? Acquisition disk. What is coming out? Fine? Thank you. Hold on. Is there any question from the online participant? Prakash, can you just check? Let me see. It's 12:30 and team manager is getting angry. Okay, let me see. See, this is a simulation of how jets are launched. Basically, this shows the magnetic field in a very tiny volume. I'm showing you. Don't ask questions. I don't know anything. You are not seeing any change? You will see now. These are realistic, three-dimensional relativistic magneto-hydrodynamic simulations of the accretion disk. As you put some magnetic field, you have a very compact dense black hole, you apply general relativity, and you start t equal to 0 to t equal to some milliamperes. That's the story. And then you see what happens. Okay? You see how jet is formed. This is a numerical simulation. Okay? Questions? Question from the online participants. Prakash, is there any question from the online participants? Okay. Yes. People who do not have any questions, feel free to go for lunch. Yes, please go for lunch. Go. Talk to me anytime. Okay, if you have question later, we can talk. Late 12:35. Okay. It doesn't look like there is any question from the online participants. So what I will do, I will stop sharing the screen and then I will log out from the group. So thanks everyone for joining, and then we will see you next time. Yes. Offline question.